Section 4.2, Formation of Waves. So this lecture we're going to look at how waves are formed, okay, and what factors affect the height and the speed of the waves. First of all, quick summary as to what creates waves. Wind is the most obvious one, dealing with the ocean. Okay? Wind, the atmosphere is moving across the surface of the ocean, and the friction between the surface of the ocean and the wind creates the waves. And generally speaking, we know that the bigger the wind is, the bigger the waves are going to be. And a physical disturbance. So that could be you dipping your finger into water. It could be a boat moving through the water, as I've got shown at the top there. Or it could be an earthquake, underwater landslide, triggering a tsunami. Okay, so wind or physical disturbance. Okay, so wind waves, these are the main ones we're going to be looking at. So the wind blows over the water, okay, which is over here on the left. Okay. As the wind starts to blow over, it produces ripples. Those ripples become chop, wind-driven waves, and they get bigger and bigger and bigger as the wind pulls more and more energy into the wave. Remember, the energy of the wave is proportional to the square of the height of the wave. So the more energy is being pushed into the wave by the wind, the more energy is going to be transferred by the wave. Now, there are four factors that affect the size of waves. Wind strength. The stronger the wind is, the more energy it's got, the bigger the wave's going to be. The fetch. The fetch is the distance that the wind has to blow over the water. Typically, harbours have very short fetches, so it's difficult for the wind to ever build up big waves, which is why it makes it a big harbour. Duration. How long is the wind blowing for? The longer it's blowing for, the more energy is being transferred to the water, the bigger the waves are going to be. And if there's any current. If the wind is blowing the waves in the same direction as the current is, you're going to get a different type of wave formation than if the wind is blowing against the current. I'm going to come back to that last point when we talk about tides. So we've got here on the left of the diagram, okay, there's the wind beginning. This is the length of the fetch here, which can be anywhere up, across the length of the swimming pool, across the width of the harbour, the length of the harbour. Hamilton Harbour's got a far bigger fetch if the wind is coming out of the southwest and west. And then you get fully developed seas, where the waves have reached the maximum possible theoretical height. And then the waves keep on going because they've got inertia. So even after they've got out of the wind field, so the wind's dropped, wave motion is, remember, inertia is related to the mass, and mass is related to density. So the waves have a lot more density, and they've got a lot of inertia, so they're just going to carry on moving. And that becomes swell. Now, swell also has got a longer wavelength, so that tends to come out first. Okay, it's shorter. This is a confusion here. I have lots of different wavelengths. Okay, confused C, lots of different wavelengths, short ones, long ones. The long ones travel faster than the short ones, so they come out first, and then these lose their peaks and turn into sort of more undulating sort of shape. So, nice image I got from a website called StormGeo. They're weather forecasters for marine traffic. So these are the summary of the wave formation. We've got the wind speed. Okay, we must have significant wind speed to produce waves. Light winds and zephyrs will produce just ripples. We need to have a distance across the water to create the waves, because the waves don't happen instantaneously, they take time to be made. And duration, how long is the storm blowing for? Now, waves come in lots of different heights, they come in lots of different shapes, so it's kind of difficult to describe, how big is a wave. So statistically, scientists and oceanographers and meteorologists use what's known as significant wave height, H for subscript S. And it's the average height, the mean height of the highest third. So you might ignore the short waves, you just take the highest 33% of the waves and then work out their average height. And that gives you significant wave height. Now, some graphs about all this. There's a lot of chaos when dealing with fluids and waves and things. It's a very chaotic system. There is some order to the chaos. So this graph on the left, you can see it literally is a scatter plot where they've measured the significant wave height for various different wind speeds. I kind of feel like this axis is the wrong way around. This is the variable that's creating the waves, and this is the variable, the dependent variable, so this should be on the axis. Anyway, never mind. So as the wind speed increases and increases and increases, the significant wave height increases. Now that's what you'd expect. Okay. The stronger the wind is, the bigger the waves are going to be. And so this is like the mean value here. And then this is probably the 95th percentile. Didn't really mention it on the where I took it from. Okay. The significant wave height is caused by the wind. Now this graph here is another scary looking graph because there's more than one set of data on there. The graph on the left is just like a standard science graph, although we tend to just plot average values. Okay. This is lots and lots of different things. What they've tried to do is they've tried to put as many different variables on as possible. So this, on the x-axis here, is the fetch length, and this is in kilometers. So we're looking, this is like 500 kilometers. That's a significant distance. And here's the significant wave height, okay, going up. So you can get an idea what the minute sort of fetch you need to generate big waves. You pick a wind speed, so we'll take strong breeze, that's about 25, 30 knots again. Okay, so we follow that curve down, and our waves are getting to be pretty significant after only about 20 kilometers fetch. Okay, so if it's blowing hard out of the north, where the fetch is essentially the bit between North Shore and North Rock, that's quite a significant fetch. That's about, what, 10, 15 kilometers. Okay, so that's likely to produce fairly significant waves. Now, of course, if you're outside the reef, the fetch is hundreds and hundreds of miles. So the waves will be bigger. So the waves will be bigger outside the reef because you've got a longer fetch. Inside the reef, it depends on the wind direction. Now, the fetch needed to generate significant seas in storm force conditions can be up to 400, 500 kilometers. But bear in mind, even with a short fetch, these waves are far, far bigger than most other waves. In a moderate breeze, these fetches are pretty small. They ramp up very fast and then they slowly level off. And the maximum fetch would be things like the trade winds, which is 2,000 kilometers or so that would for the ocean. So swell, what is swell? Well, we talked about swell before. Swell is essentially the residual waves that are left over once the wave has progressed outside its wind field. So the wind has created the waves. Now either the wind drops or the long wavelengths have travelled outside because they're moving faster, have travelled outside the wind field. And you lose the sharp tops of the waves. Obviously this is not a sharp boundary between but you lose the pointy tops. So the pointy tops of wind-driven waves disappear as gravity sort of flattens them out, and they turn almost sinusoidal. And because you've got rid of the shorter wavelengths, and you tend to get much more regular waves. So this image on the right is showing pretty regular swell coming in, and there's no significant wind in this picture at all. Okay, so you've got no wind and you've got no wind-driven waves, but you've got this remnants of the swell left over from maybe a big gale at sea or something like that. The image on the left is kind of a fun one. Sailing in swell is kind of hard, as you get the wind-driven waves over the top of the swell superimposed. And when you're at the bottom of these swells can run to quite a few meters in height. If you get to the bottom of the swell, the sails don't get the wind anymore, so you can slow down. So sometimes sailing in swell is quite challenging, especially if the wind is light. You might not have enough power to be able to carry the boat up the other side of the wave. It tends to be quite nausea-inducing for people who suffer from seasickness. So rogue waves. I'm going to be putting a cut in here for a simulation. Rogue waves happen at waves that far exceed the significant wave height. So this is a series of waves measured by an oil platform in the North Sea, and then there was this huge great wave here that was much, much higher than any of the other waves forming. Okay, so significant wave height was around here. And then you had this, and this is called a rogue wave. Now, the chances of that happening are quite low, and for a long time they were stuff of legend, but people who encountered them generally didn't survive. It's caused when two waves interfere. So if you've got two series of waves, and the crests happen to coincide, you get a very much bigger wave. And so that's been caused by that. And I'll be showing that in a simulation. This is the research ship Discovery. She recorded a big wave of 29 meters high, which is really big. This is a computer simulation done by a physics bunch. It's called OPhysics. They're doing lots of other fun physics simulations for those of you who are interested in physics. What this is showing is that if you have two waves, we've got this lower wave here, we've got this taller wave, when you add them together, so when the waves coincide with each other, we get a bigger one. And this is how rogue waves are formed. So let's run the simulation. Let's finish running it. Okay, so waves come in, coincide, and then they carry on going their way again. So the two waves are just going and doing their thing and pretty much ignore each other. But let's imagine the two lumps of water are now on top of each other, so you've got much higher water. And you can, if you make both pulses maximum height, then you're going to get a much bigger wave. If you make, if you have, for example, a oops, you can make a negative from that. So let's have the yellowish one, I think it is, as being a wind-driven wave, and the blue one can be like an ocean swell. And look what happens when they coincide. So the wind-driven wave goes on top of the ocean swell, and the ocean swell got bigger. You can, I've just seen that you can make these negative. In that case, you can get weird effects happening like this, where the two waves essentially cancel each other out as they go past. Okay, so I've put a link for this on OPhysics, so you can see it. I think I put a link on the video we've got already. So superposition. Okay, when two waves coincide, the crests coincide, you get a bigger wave. So if you've got two very big waves coinciding simultaneously at a certain point in space and time, you're going to get a gigantic wave, and that's why Prave's called a rogue wave.